As we start into Chapter 2, the topic is functions and models. So if you enjoyed Algebra 2, this is a chapter you're going to like. We're going to be doing lots of things with functions, regressions, slopes of lines, and things of that nature. This first section, there's actually 4 objectives, if you notice here. It's numbers 1 through 4. So first thing you're going to do is identify independent and dependent variables in a scenario. This is something a little new, but not too difficult. Second, evaluate functions given numerical input values, which you did in Algebra 2. And then evaluate functions given a binomial expression as an input value. Again, you've done this in Algebra 2. And the fourth one, determine if a relation or a graph is a function using the vertical line test or mapping. Again, this is nothing new. So I think you'll find this section more review, and let's just dive right into it. Now the first thing we need to do is just define some vocabulary. When we talk about what is a function, the first thing we want to say is a relation. Know that a relation is just a set of ordered pairs. And this notation right here, I have 2 ordered pairs listed. I should have these brackets right here. That mathematically is shorthand for a set. So this set here of ordered pairs has 2 ordered pairs in it. This is considered a relation because it's ordered pairs. Now the independent variable is the first variable in a relation. And typically in our setup here, we're going to have this written as XY ordered pairs. So therefore we would say the independent variable is the X value. Or another word you might be familiar with is the input. You choose or you input your X. When you put in your X, you actually get the output, which is the Y value, and that is called the dependent variable. And it is the second variable in a relation. Again, typically we define it by the letter Y. It just depends how these ordered pairs are written. And another word for that would be output. Now the definition of a function is you're going to actually look at a relation to see if it is a function or not. It may be a function and it may not. A function is a set of ordered pairs x and y in which each first component is paired exactly with one second component. So for example, I might have this set of ordered pairs 1, 2, 3, 7, and 5, 6. And what it says is for every x value, so for the 1, for the 3, or for the 5, for every x value, it's paired with exactly one second component. So the 1 is paired with the 2, the 3 is paired with the 7, the 5 is paired with a 6. Never do we see another 5 come into play, for example. If there was a 4th ordered pair, if we had another 5, and this time the answer was the ordered pair 5, 1, that would make it not be a function because for each, it says for each 5, or in this case for each 5, there's exactly one second component. In this case, there's 2 second components, a 6 or a 1. This means this particular relation is not a function if I add this blue ordered pair. Now, if this blue ordered pair was not here, then the 3 ordered pairs written in red would be defined as being a function. You may also be asked to state the domain and the range. The domain and the range just go with independent and dependent variable. Remember, domain and range is alphabetical. We have X comes before Y as domain comes before range. So the domain and the range, the domain is just the list of the X's, the range is the list of the Y's. And let's just look at these 3 red ordered pairs that I wrote down. If I asked you to state the domain in here, again, maybe a vocab, we would say domain is the X's or the input. Another word I might say it's the independent variable. Sorry. In this case, our domain would be comprised of the number 1, 3, and 5. Now the range, definition of range, is just the Y value or the output. Or a new term we learn today is the dependent variable. And in this case, it's the listing of the Y's, which here we have a 2, a 7, and a 6. Now I want you to take a moment and take a look at these two different relations. We have the F relation and we have the G relation. I want you to pause the video and determine for me, are either one of these two or both of them considered to be functions? So pause the video, take a moment and determine, is F a function and is G a function? Hopefully after you've looked at that, you determine that the first relation is actually a function. Again, definition of a function, for every x value, there's only one output. So every time I put in a 1, in this case, I get a 2. When I put in a 2, I get a 4. When I put in a 3, I get a 6. G is not going to be a function, and it actually breaks right here with these two ordered pairs. In this case, I put in a 1 and I got a 2. Not a problem. But the second time I put in a 1, this time I got a 7 back, which means this would not be considered a function. On here, they're going to ask you to list the domain and the range. And the one thing I do want to highlight is this. If I were to list the domain, what you want to do is keep two things in mind. You always list the values in numerical order or in increasing order, and you never list repeats. So the domain for this function, I would say, is 5, 6, 7, and 8. And I'm going to put that in set notation. The range in this function, be careful. The number 3 happens twice and the number 1 happens twice. You just list them one time, so I would say the range is the number 1 and the number 3. Now this slide here is just a little bit more vocab. Here's another way of talking about a function. A function is a correspondence between two sets A and B, in this case all of our x's and all of our y's, in which each element of A corresponds to exactly one element of B. So I just wanted to have you be familiar with seeing the function definition in more of a true mathematical notation. All right, let's review one thing, sets of numbers and how that works. Let's talk about a real function first. If I say we have a real function, that means it's a function whose domain and range is a set of all real numbers. Okay. And that's just literally as simple as that. Now, what are real numbers? Remember, real numbers, which are right here, are all the numbers on a number line. So you can put them on a number line. Any number on a number line. Well, if you think of a number line and I ask you to graph, you know, these are various tick marks. Let's have this 0, 1, 2, -1, -2. If I ask you to graph the number 1, clearly you can do that. It's on a number line, therefore it's a real number. Can you graph the number 0.5? Sure, it's right there. It's a real number. How about the number -2/3? Sure, -2/3 is roughly going to be there. How about the square root of 4? The square root of 4 is the number 2. It's right there. So it doesn't matter if you have a decimal, a fraction, a radical, a whole number. Those are all considered real numbers. Okay. Now, what you want to think about now is how do we break those numbers down? They can also be called, numbers can be called integers. Now, integers are positive and negative whole numbers. Okay, so positive and negative whole numbers, including the number 0. Those are called integers. Shorthand for an integer is the capital letter Z, and it looks like this. What you do is you write it like that, and you kind of do a second line like that. Okay. By the way, the shorthand for the reals, it looks like this. It's a capital R with an extra line right there. I am absolutely fine on homework or test if you told me that the numbers are all real. If you use that notation, I'll give it to you. If you think they're all integers, write the Z with that. That's just fine. The third type of number we want to talk about are rational numbers. And these are all real numbers, so I'm going to shorthand, real numbers that can be written as a fraction. Okay. If you cannot write a number as a fraction, it is not considered to be rational. However, it could be a real number. A nice example is this, the square root of 2. The square root of 2 Clearly, I could write it as a fraction, put it over 1, but that's not what they mean. They mean something like this, 0.5. Is 0.5 a rational number? Can you write 0.5 as a fraction? Sure, that's 5/10. So what I could say is that's the same as 5/10. That's also the same as 1/2. It can be written as a fraction. So the decimal 0.5 is a rational number, and it's also clearly a real number because I can put it on the number line somewhere. This right here, though, the square root of 2, I can't write as a nice fraction, okay? So this is actually not a rational number. This is a really good case of what's not rational. Another number that's considered not rational is the number pi. Pi cannot be written as a fraction because it never terminates and it never ends. Okay. The last number I want to, and by the way, shorthand for that is just a letter Q, like that. And then the last set of numbers are the natural numbers. Natural numbers are the numbers that we actually see kind of in nature, and they are basically a subset of the integers. What natural numbers are positive whole numbers and the number 0 also. Okay. So natural numbers, again, are things that are in nature, kind of is how they would simulate or kind of associate that. So natural numbers are part of integers. Integers are part of rational numbers, and rational numbers are part of real numbers. So if I wanted to break this down, let me just show you one last slide on this and we'll move on. A good way of doing this would be this. It would look something like this. This is kind of how they're all embedded. The majority of numbers we deal with are real numbers. Again, they can be put on a number line. And then we get into rational numbers. Or again, rational numbers are those that can be written as a fraction. There are some real numbers that you can't write as a fraction. Those sit out here. So those are like the square root of 2s, the pi's, things like that sit out in the reals that aren't rationals. There's also numbers that can be integers that fall into the rationals. So, for example, the fraction 2/3 is not an integer. It's not a positive or negative whole number, but it's rational. And then natural numbers are a subset of integers. Integers are positive and negative whole numbers including 0. Natural numbers are just positive numbers and 0. So one that sits as an integer but not a natural, for example, could be the number -5. That's an integer, but it's not a natural number. Now, back on the slide where we defined real functions and things of that nature, there was something called a member of a function. A member or an element. Okay. A member or an element, by definition, it says if x is said to be in a certain set, a set A. So, for example, when we talk about member or element, here's shorthand math notation. If I said let x be the number 5. The number 5 is an integer. It's a positive whole number. So what I could say is x is an element of the integers. And this is shorthand for that. This is shorthand for an element. It's a little e, and this is part of an integers. If you're comfortable with it, you can definitely do shorthand math written like that, or you would just write the sentence out that x is an element of all the integers. Okay, let's get to another objective. This objective talks about defining independent and dependent variables. Remember, independent is the input or the x, dependent is the output or the y. Here's our scenario. A bakery charges $2 per muffin. Customers get a $2 discount for every 6 muffins purchased. Which statement is true to say? Is cost is a function of the number m of muffins, or is the number m of muffins is a function of the cost? One of these two statements is the right relationship. And I'm going to tell you, for this case here, the correct answer is going to be the first statement. The cost is a function of the number of muffins. Okay, so the cost is determined by how many muffins we have. That in itself is telling me which one is the independent variable. So if I say which is independent, which one when you go to the store do you typically choose? Do you choose how many muffins you want to purchase, or do you choose how much money you want to spend in general? Okay. Typically, you're going to go to the counter and you're going to tell the person how many muffins you want. That's your independent variable. So the independent variable is the number of muffins. Therefore, the cost is dependent, this should be with a T, on the number of muffins. So cost is your dependent variable. Now, we know that the independent variable is the input or the X. That means domain. The dependent is the output or the Y. That's the range. Now, this is a real life example. So think about this. If the number of muffins above, we said actually could be symbolized by the letter M, what would you say is the domain of this particular example? When you go to the store, what are your possible options of how many muffins you're going to order? All right, you're probably going to order either 1 muffin, 2 muffins, 3 muffins. Assuming they're not going to let you order 3.5 muffins. You have to order a whole muffin. You possibly could order 0 muffins, by the way. Maybe you're just going to talk to someone and keep them company. So the domain of this function, we would say, is all the m's are either going to be greater than or equal to 0. But what's special about this case? The m's, this is shorthand, are all elements of integers that are positive. Now, for most of you, you do not need to know how to write this shorthand. This is more, if you want to know that shorthand, you can use it, okay? That's what this says. M is an element of all the positive integers. So 0, 1, 2, 3, 4, and so forth. Now the range is the cost. The cost structure for here, again, it's $2 per muffin, and you can get a $2 discount for every 6 muffins you purchase. So you need to think about, will you ever need to have some change? Or are these just going to be bills that I'm using? Okay. The cost of these muffins is always either going to be $2, $4, $6, $8, or what have you. So the range for here, they said let C be cost, fine. We're going to say this cost is either going to be greater than or equal to 0 because I may buy no muffins, which means the cost is 0, or I may buy more. In this case, I'm going to say the cost is also an element of all of the positive integers, is just the shorthand. Now, again, a relation is a set of ordered pairs. When we determine if it's a function, there's 3 things we can either do. We can look at tables or ordered pairs. Okay. We may also look at words or equations, is how functions can be represented, which we just saw a function back with the muffins. And a third way is from a graph. Now, I want us to take a look at this scenario because it's kind of tricky to set up at first. This n here is our input, by the way. Okay, this is our input. This is our independent variable. Independent input kind of all goes together, right? They'll start with an in. Here's a scenario, and think about what the output might look like. Let n be an integer with n is greater than or equal to 2. So they've started out the table. N either has to be 2, 3, 4, 5, or larger. Graph a function that shows how many elements of an ordered set of n different integers are greater than the median of that set. Okay, so what this says, this is kind of tricky. How many elements of the set are greater than the median of that set? So that's going to be our output. And I'm just going to put that over here. The output or the dependent variable. And I'm going to put what the set looks like here. This tells me the set has to have 2 elements. So I have to have a set such as 2 elements. It's important to realize they say they all have to be different integers. And they have to be integers. Okay, fine. A set of n different integers. What if I pick the integer 1? And I need 2 numbers in my set. So 1 might be a number. Another 1 can't be there. They have to be different. Maybe it's 2. So that's 2 elements are in my set. The question is, how many of these numbers in this set are larger than the median of this set? Okay, well, median means the number in the middle. Well, the number in the middle, when there isn't one right smack in the middle, remember, you add up the 2 and take the average. So 1 and 2 is 3. The median is 1.5. How many of these numbers are larger than 1.5? One of them. It's this guy right here. So 1 is my answer. Okay, the third one, come up with a third set of numbers, or with 3 numbers. Fine. I'm going to pick 2, 5, and 8. Just pick some other ones. That's 3 elements. I want to find the median of this set. The median of this set's easy. It's the number 5. How many numbers in this set are larger than 5? Well, 1. It's 8. That's my answer, is 1. 4 numbers. Fine. Let's look at another set here. What if I pick 1, 6, 8, and 9? The median is going to be the average of these two. 6 and 8 is 14, divided by 2 is 7. How many numbers are larger than 7? 2. Let's look at another one of a 5. I'm just going to pick 1, 3, 6, 10, and 12. The median is the number 6. How many are larger than that? 2. Okay, what do you think is going to continue to happen? Well, I'm going to tell you there's going to be a pattern. It's going to end up being 3, 3, 4, 4, 5, 5, and so forth. Okay. Now they want us to graph this function. Fine. The first output I have, the input and output, is the ordered pair 2, 1. So at the ordered pair 2, I'm going to do 1. The next is that when n is 3, I have 1. So 3, 1. Next is 4, 2. And then 5, 2. And I realize there's a pattern. So it's going to be 6, 3, 7, 3, 8, 4, 9, 4, 10, 5, and so forth. And that is graphing this function. One thing we haven't touched on yet, but we can easily do, I can graphically tell that this relation actually is a function. They told me it's a function, by the way, right here. The function you can visually tell in a graph because it must pass, remember this, the vertical line test. Vertical line test means you drop a vertical line anywhere and it only crosses at most 1 point. If I dropped a vertical line here, it crosses once, 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 once. I can visually tell that this is a function. Now here in this next example, we actually have an exponential function already graphed for us. This is the equation of the function. They want us to state the domain and the range of this while it's in an equation format. Fine. The domain are what the x's can be. The range is what the y's can be. Okay. Now in this case, the domains, if we look at the various ordered pairs, here's an ordered pair right here. It looks like roughly the ordered pair 3, 4. Here's another ordered pair, it looks like. 0, -3. Okay, and I might be able to find some other ordered pairs. Now, what they don't want you to do in this case is say, oh, the domain can be the number 0, and 3, and 4, and 5, because this function continues on forever. Look at this right here. There's an arrow, and here there's an arrow, which means it goes on forever. The domain of this function, you want to think about this. What can x be? Well, can I choose 1 for x and land on the graph? Sure, I land there. 2, I land here. 3, I land here. 4, I land here. -4, I land here. Is there ever a number that I choose for x here that will not give me an answer? Look at the graph. If you graph it and this graph doesn't have any breaks in it left and right, the answer is the domain x is all real numbers. And that can be my final answer. Okay? Or another shorthand you could do, x is the element of all reals. Or you could just write out in an equation format or a sentence, x is all real numbers. That's fine. Now the range. The range is the y's. The range is the output. It's right there. Well, what axis? The y-axis is right here. It goes up and down. So when you're looking at a graph, when you're determining the range, you're determining the height of this graph. Okay. When you did the domain, by the way, the domain is all the inputs or the x's. You just visually look at it left to right. If I read this graph left to right, if I go this way, I'm going to notice it continues on and on forever. The range is unlimited. That's why I said it's all reals. Or I'm sorry, the domain is unlimited. But look at the range. The range is the output or the y values. It's the height of this graph. The height of this graph, we have an issue. It doesn't start until about right here. This thing has what we call an asymptote. So the asymptote for this graph, this function starts, it looks like roughly at -4. But it's not quite at -4. So what we write is the range is all the y's greater than -4, but it does not include it. So do not have the =2 sign there. Again, I already mentioned this. A test, if an equation is a function, is the vertical line test. Let's just save you some time here. We have two graphs, two equations. Get your graphing calculator out. Put this in your graphing calculator. I'm going to give you a quick sketch. This guy right here is going to look something like this, roughly. Okay? This guy over here is going to look, let me fix this a little bit. Something like that. Okay, the domain and range of this function. If we look at this parabola, y equals x squared minus 4, I want you to pause the video and figure out how would you write the domain and range, and then do the same for the second graph. So pause the video, write the domain and range, and see if your answers are correct. All right, here's what you should have gotten. Remember, for the domain, what you want to do, since this is the x-axis, you visually just look at the graph left to right, which is how it looks. This graph, yes, it doesn't have anything over here in this space or over here in this space, but it does have answers for x at these values. I could put 10 in there and graph somewhere up here. It would be way up here. So the domain for this function is all reals. I can put anything in for x and get an answer. My calculator's not going to say, wait a second, if you put 30 in for x, 30 squared minus 4 is going to say no answer, I can't calculate it. Of course it can do 30 squared minus 4. Okay, so the domain is all reals. The range, this thing actually has its vertex at the number -4, so it does include it. So be very careful. The range is the height. It's the y-axis. So look at the graph up and down. Well, this thing doesn't start until -4 and everything higher than -4. So that's why the range, which is the output or the dependent variable, is y is greater than or equal to -4. Now the second graph over here is our exponential function. This one here, what can you put in for x? Can I put a -1, a -2, a decimal, a fraction? Absolutely. The range for this function is all real numbers. I just wrote it differently. I put x as the element of r. That's fine. Or just write x as all real numbers, like in one long sentence. That's fine. Now the range of this function, you have to be careful. My graph is a little off. So if you graph yours, you're going to notice it's a little bit down further and then it comes up. The height of this graph is the range. You're going to notice this graph doesn't start until a little bit after 0. So it's all the y's greater than 0. Okay? Exponential functions have asymptotes. These are vertical or horizontal lines they get close to but never quite cross. Be careful, this thing has an asymptote on the axis. It gets close to 0 but never quite gets there. Now we're almost done. This slide is a pretty easy one. This notation right here, just know how to say it. It is said as f of x is how you say it. Okay. Here's the question. Suppose f is the function defined by this rule right here. They call it a rule. You guys, it's an equation. It's in function format. It's the same thing. And they're saying for all real numbers x. So they can put any type of real number in an x and get an answer. They want you to evaluate f of 5. Fine. That's easy enough to do. It's not hard. Know how to do this without your calculator though, you guys. What you would do is put 5 in for x. So I go over here where the x's are and say f of 5 is equal to 4 times 1/2 to the 5th power. Okay, be careful, you guys. What this means in exponential format is the rule you learned last year is you can distribute that and do PEMDAS. Always do parentheses, then exponents, and then multiply. So do not multiply this thing by 4 until the very last end. PEMDAS. Okay, parentheses and exponents. That's our first, and then we'll come back and multiply. So this is going to be 4 times 1 to the 5th power over 2 to the 5th power. 1 to the 5th power means do 1 5 times. So 1 times 1 times 1 times 1 times 1 is 1. So that's 4 equal times 1 over 2 to the 5th power. That's 2, not 10. It's 2 5 times. That's 32. Multiply straight across. The answer here is 4 over 32. We would always simplify that fraction. The answer to this is the fraction 1/8. And I'm going to tell you, on a test, you need to be able to do this without a calculator. Your calculator, the test will not allow you to use a calculator for this. You need to keep it in fraction format and show me how to do this. This is basic math from Algebra and Algebra 2. Okay, part B is an interesting question. They want you to determine, is f of negative 2 plus 3 the same as f of negative 2 plus f of negative 3? Basically, can we distribute function notation? Is the big question. I want you to pause the video and just think about this for a second or two, and then when you're done pausing it, I'm going to pop the answer up and you're going to see if they are equal or if they're different. So go ahead, pause it and think about this for a second. Here's what we have. When you do the math, what you need to do on this side is realize that you do parentheses first. So they actually want you to find f of 1. F of 1 is the answer 2. The right-hand side, you need to find f of negative 2, and you need to find f of 3. F of 3 is pretty straightforward. It's right here. That actually, f of 3 is going to simplify down to 4 over 8 or 1/2. Okay. Now be cautious on f of negative 2. This is a good review. If I put negative 2 in here, I can now distribute it through, which I get this side here. Now a negative exponent, to get rid of it, you just flip-flop it across the fraction bar, and I have this. 2 squared is 4. 4 times 4 is 16. So it's 16 and 1/2. What this shows us, by the way, folks, is function notation is not distributive. We clearly get two different answers, so be very careful. So last slide, and what they want you to do here with the same function is evaluate f of q plus 1. Fine. This used to be f of x, by the way, folks. So notice they replaced x with q plus 1. So you go in wherever x is, and you replace it with q plus 1. It's as simple as that. So f of q plus 1 is equal to 4 times 1/2 q plus 1. Now, we're going to get into more details on how you can pull this apart. For now, I'm just going to have us keep the function in this notation, and that's all you're going to have to do. If you do recall, though, this property of exponents is going to tell me that I can rewrite this, by the way, as 4 times 1/2 to the q power times 1/2 to the 1 power. And then I can combine the 4 and the 1/2 and get 2. So this simplifies to 2 times 1/2 to the q power is what they want you to take away from that. Again, I'm okay right now because we will get into this breaking down later in the year. If you're successful on the entrance card, this is going to be your modified assignment. Everyone else, this is it. And just do pay attention in class to see if I justify any of the problems. Good luck on the homework.